Okay, thank you, Jenny. So great to see everyone after this like a 3 month gap, like a break during this winter break. And so this is the first seminar, PPAI seminar in 2021. And this week, yeah, let me wait a little bit longer because I see people still joining this webinar room. So this year is this week actually is the Chinese New Year week. So as wish everyone have a great the year of ox and. So I think that this talk is a really timely report and talk and a contribution from our speaker today, Mitch Bushuk. And the reason is that last summer, 2020, we had a really bad melting in the Arctic. And so I think our panel member really want to know what has happened there and what's going on there and how to understand this and how our model did a prediction for that event or in the other event in the past. So it's a really timely update from Mitch. And another thing I think is Mitch, because he's working really front line of this CS prediction and in GFDL. And from his CV, you can clearly see he's now the research scientist and leading some project to improve a CS prediction, CS predictability, and the polar oceanography, and particular over this seasonal and interannual timescale. And he's currently working on this the model, simulation, observation, monitoring, and using a different version of a GFDL model, and conduct a lot of experiment and share with for the community, such as like a lot of control run and initialize prediction in sample and data simulation runs and historical simulation. And in GFDL, his product used to participate in many model comparison project like the ARCUS, CS Outlook project, and many others. I don't want to repeat here. And so before Mitch joined GFDL in 2015, he got his PhD degree from New York University in the mathematics and atmosphere and ocean science. And so, yeah, I think it's time. I probably say too much, so it's time to start this, and I will pass it to Mitch. And please join me. Welcome Mitch to give this the new update on this CS prediction.
Great, thank you, Qinghua, for that nice introduction. In today's talk, I'm going to be speaking about Arctic sea ice prediction, and my goal is to give you sort of an overview of the current skill of modern sea ice prediction systems, talk about the inherent predictability of Arctic sea ice, and also give you some perspectives on sort of future prospects, where we're heading with this work going forward. I would just like to start off by acknowledging contributions from many, many co-authors. You can see a long list of names listed here. I don't have time to read them all, but there's been a lot of people that have contributed to what I'll be speaking about today. So a big thanks to all my co-authors, and that's what makes this stuff fun. Okay, next slide. So the starting point for today's talk is this now very iconic curve of September Arctic sea ice extent. So over the satellite era, which is now 41 years long, we've observed a very strong decline of Arctic sea ice extent. But in addition to the decline of Arctic sea ice, we also notice that there's a lot of interannual variability in both the summer as well as the winter extent of Arctic sea ice. And it's become very clear in recent years that there's a lot of interest in many communities in our ability to predict these large interannual fluctuations that we see in sea ice. So there's really been this emerging need for seasonal Arctic sea ice predictions. These predictions could potentially be useful for a wide range of different stakeholder groups, such as northern communities, shipping industries, fisheries, wildlife conservation, ecotourism, oil and gas industries, and scientific logistics. And so in this talk today, I'm going to attempt to answer 3 different questions related to Arctic sea ice predictions. Can we, have we, and will we? And I'm borrowing this framework from a really nice paper by Libby Barnes and James Screen, who used a similar framework to analyze the mid-latitude jet stream and the possible influences of Arctic sea ice on the jet stream. And so in the 3 parts, I'm going to start with can we. And so I'm going to first present the scientific basis for sea ice predictability. So why do we think predicting Arctic sea ice is possible. In the second part, I'm going to look at the have we question, and I'm going to quickly summarize the performance of current modern sea ice prediction systems. And then in the will we part, I'm going to take an eye towards the future, and I'm going to drill down a little bit deeper onto a specific topic and focus on this spring predictability barrier that exists for summer sea ice predictions. Okay, so let's dive into this first question of can we? So there's a number of different sources of predictability for Arctic sea ice extent that have been identified in the recent literature. And I'm just going to go through a sort of a list of these sources of predictability in the coming slides here. So the first really important source of predictability comes from radiative forcing. So if you take a modern GCM and you force it with observed greenhouse gas concentrations, aerosol concentrations, and other forcing agents, what you find is that most CMIP6 models are capable of reproducing the observed sea ice decline with a reasonably good fidelity. So the gray line on here shows the CMIP6 multi-model ensemble mean. The black line shows the observations of pan-Arctic sea ice extent. And you can see that the models are doing a fairly good job at capturing this decline in Arctic sea ice. Now, there are a number of issues with these CMIP6 simulations, but in terms of this sea ice decline, they're doing a reasonably good job. Now, the plot on the right is showing large ensemble historical simulations performed with the CESM model. And you can see that within a given GCM, there's a large amount of variability in the simulated trends within a given model. And this is very important to keep in mind when we're assessing our models, is that there's a huge amount of internal variability of Arctic sea ice trends. And this observed record is only sort of one realization of a very chaotic system. Okay, so in addition to this longer term trend, there's a lot of predictability coming from seasonal to interannual mechanisms in the climate system. And one really important source of predictability comes from the simple persistence of sea ice extent anomalies. So what we're looking at here are lag correlations of sea ice extent in different initial months and correlated with future sea ice extent anomalies. And what you can see is that there's sort of an inherent 2 to 5 month memory of initial sea ice extent anomalies. And you can imagine that there's going to be some associated sea ice predictability associated with this memory of sea ice extent. Another key source of predictability comes from the thickness of sea ice. So if we look at a typical sort of spatial autocorrelation of sea ice thickness anomalies, what we see in these two plots on the top row here are that thickness anomalies tend to be very large scale. So a typical spatial scale for these thickness anomalies would be thousands of kilometers. And we also see that in GCMs, thickness anomalies have a very long time scale of persistence. So in most GCMs, there's a lot of multi-annual persistence of sea ice thickness anomalies, which can be visualized by this black curve here. And typically the thickness anomalies have more persistence than sea ice extent anomalies do. So the fact that we have this long timescale persistence and also this very large spatial structure implies that there's quite a bit of predictability to be potentially harvested from sea ice thickness. Another key source of predictability comes from the upper ocean. So on seasonal to interannual timescales, upper ocean heat content anomalies are very persistent. And these upper ocean heat content anomalies can interact with the sea ice edge, especially in winter. And they can modulate the rate of growth of sea ice. So for example, if the ocean is anomalously cool, you're going to tend to promote sea ice growth. Whereas if the ocean is anomalously warm, you're going to tend to reduce sea ice growth rates. And what we see is that if you look at ocean heat content, it's generally negatively correlated with sea ice extent, both in terms of the long-term trend, but also in terms of these interannual fluctuations that we see as well. So you can imagine that this might be a key source of predictability for the sea ice edge. Now, sea ice is also strongly forced by the atmosphere, both dynamically as well as thermodynamically. And because of this, atmospheric modes of variability are also a key source of predictability for sea ice. For example, on the left here, I'm showing the spatial pattern of the NAO, the North Atlantic Oscillation. And so the NAO tends to produce these dipole anomalies of sea ice concentration between the Labrador Sea and the Gin and Barents Seas. And in recent years, there's been some really exciting work coming out of the Met Office, which has shown that it's possible to skillfully predict the wintertime NAO on the seasonal timescale and possibly even on the sort of interannual timescale. And so if you can predict the NAO skillfully via the NAO's impacts on sea ice, that may also give you some predictability for sea ice extent as well. Another key source of predictability comes from the large-scale circulation of the ocean. And one prime example of this is the Atlantic meridional overturning circulation, the AMOC. So AMOC typically has a lot of persistence on the seasonal to interannual to decadal timescale. And there's been some nice work done recently that has documented sort of a chain of mechanisms that could connect AMOC variability to sea ice changes. And so specifically when AMOC fluctuates, it changes the heat transport through the North Atlantic Ocean and ultimately through these flux gates into the Arctic basin. And then that modulates the amount of heat that gets delivered both laterally as well as vertically to the sea ice, and that will modulate sea ice extent and volume anomalies. So you could imagine that if you can predict AMOC skillfully, you may be able to also predict sea ice skillfully as a result of this interaction. Another really key aspect of the sea ice predictability literature comes from these so-called perfect model predictability experiments. And in these experiments, we seek to ask the question of what are the upper limits of Arctic sea ice predictability? And so the idea of these experiments is to take a GCM and take an initial condition and add a very small perturbation to the initial condition and run an ensemble of simulations forward in time. Now, as you run this forward, the ensemble is going to spread out under the chaotic dynamics of the system. But then you can play a game where you take one of the ensemble members and you call that the truth or the observation. And you ask, how well can my other n-1 ensemble members predict this truth member? And then doing that, you can compute a sort of prediction skill metric, like an anomaly correlation coefficient or an RMSE, for example. And what that gives you is the upper limit of prediction skill achievable by that model. And it's an upper limit in the sense that we're assuming perfectly known initial conditions and perfectly known model physics. So there's been a lot of papers that have done this in the last 10 years or so. And this slide's very busy, so I don't expect you to actually absorb the individual plots. But the key message I want to leave you with is that these perfect model predictability experiments estimate that Pan-Arctic sea ice extent should be predictable somewhere between 12 and 36 months in advance. So there's quite a long predictability horizon for Pan-Arctic sea ice extent, as estimated from these GCM experiments. And so, kind of putting this all together, there seems to be a lot of different reasons that we'd expect Arctic sea ice to be predictable. You know, these perfect model experiments suggest it will be. It interacts with the ocean and the atmosphere, which have predictable components. There's aspects of the sea ice itself that are predictable, you know, its extent and its thickness. So we have good reasons to think that the answer to this can we question should be yes. So now I'm going to move on to the second part of the talk, which is this have we question. So I'm going to show you, at least briefly, kind of how we're doing in terms of our current modern sea ice prediction systems. So on this slide, what I'm showing you are some results from a newly developed system from GFDL called the GFDL SPEAR system. This is a dynamical coupled seasonal prediction system. And so it's based off a coupled global atmosphere, land, ocean, sea ice model. And this model is initialized using a bunch of different data types, specifically TNS temperature and salinity profiles in the ocean, satellite sea surface temperature observations, atmospheric temperature, winds, and humidity. One point to make here is that this system does not currently assimilate any sea ice data directly, but the sea ice state is quite well constrained by the assimilation of atmospheric temperatures, winds, and sea surface temperatures. And then using this system, we ran a whole suite of retrospective seasonal predictions. So these are ensemble predictions initialized on the first of each month and then run for 1 year of time. And on this plot on the left here, I'm showing our predictions of September Arctic sea ice extent with the observations shown in black here. And then the colors indicate predictions at various lead times, going from September 1st back to June 1st. And you can see that we're skillfully capturing the trend with reasonable fidelity. But then the exciting part, to me anyways, is that we're also getting some of these interannual fluctuations in sea ice with some skill. And if you look at the anomaly correlation coefficients in color here, you can see that we have some skill. And the values in parentheses indicate the detrended anomaly correlation coefficients. So if you first remove a linear trend from both the observed and predicted time series, and then compute a correlation, you get these detrended correlation values. And you can see that, so we also have some skill at capturing these detrended fluctuations of sea ice relative to that linear trend line. Okay, so over the last decade or so, there's been a number of groups around the world that have developed these dynamical seasonal prediction systems, and they've assessed the ability of these systems to predict detrended Pan-Arctic sea ice extent anomalies. And these studies have found that Pan-Arctic sea ice extent is predictable 0 to 6 months in advance, with the skill horizon depending quite strongly on the system you're looking at, and as well as the target month you're trying to predict. So in these plots, target month refers to the month that we're trying to predict, and then forecast lead time refers to the number of months prior to the target month that the forecast was initialized. So as you move up these plots, you can see that the skill values tend to decay. And we see that there's some kind of broad similarities between the various systems. There tends to be fairly high skill at lead times of 0, 1, and 2 months. But then some systems have higher skill in winter than in summer. Other systems have slightly higher skill in summer than winter. So there certainly are some differences you can pick out here. So there's also been some really exciting work based on different sort of statistical model techniques for predicting Arctic sea ice extent. And these techniques have shown that Pan-Arctic sea ice extent anomalies can be skillfully predicted 0 to 4 months in advance. And these various techniques use all sorts of different predictors to form these predictions. For example, this study uses spring melt pond coverage over Arctic sea ice. This study uses the area that gets dynamically advected out of a given region as a predictor. This study is based on a bunch of multivariate EOFs that use sort of large scale atmospheric fields and SSTs as a predictor. And essentially all these systems also use the satellite sea ice concentration record as a predictor as well. And the skill horizons are fairly similar to what we get with the dynamical models, but generally I would say the statistical models tend to have slightly higher skill, but a very careful comparison has not been done yet. And we're actually we're planning to do that in the coming years. Okay, so everything I've shown so far has been for Pan-Arctic sea ice extent, which is the total sea ice extent within the whole Northern Hemisphere. Now, of course, for any sort of user of these predictions, they're going to be much more interested in sort of local or regional scale type information. And so at GFDL and also many other groups in the community have been doing this as well. We've been taking the Arctic and we've been chopping it up into these 14 different regions of interest, and then asking whether or not our systems are capable of capturing interannual variability skillfully on these smaller sort of regional scales. So here I'm showing some results from another system that was developed at GFDL. This is the GFDL floor system, which is actually now sort of our previous generation system. We've recently transitioned to this new GFDL spear system for our seasonal predictions. And what we found is that the answer tends to be yes. The system does have skill at capturing regional sea ice extent anomalies, and the skill varies quite strongly depending on the region you're looking at. And what really stands out is if you look at the regions of the North Atlantic, so in particular, the Barents Sea, the Jin Seas, and the Labrador Sea, we find that in each of these regions, for predicting winter sea ice extent, we have skill going back to beyond 6 months in advance. So we have quite high skill for winter sea ice. Anywhere you see a triangle on these plots indicates that the skill of this system is exceeding that of an anomaly persistence forecast. So we're generally capturing additional sources of skill beyond just sort of the simple persistence of sea ice extent anomalies. Now, if you compare this with the North Pacific sector, if you look at the Bering Sea and the Sea of Okhotsk, you can see that the skill is generally quite a bit lower on that side of the Arctic. And we don't have much skill beyond 3 months in advance or so, at least in this prediction system. Now we can do the same sort of analysis for the regions of summer sea ice variability. And so summer sea ice tends to vary most strongly in the Lapte, East Siberian, Chukchi, and Beaufort seas. And we see that in those regions, the system has skill at lead times ranging from 1 to 4 months in advance. And one thing that really stands out in these plots that I think is quite an interesting feature is that if you look at the Lapte and East Siberian seas, the skill tends to have this sort of diagonal correlation structure to it. And in these plots, diagonal lines correspond to common initialization months. So what this is saying is that if we initialize a forecast from May 1st or later, we can skillfully predict summer sea ice extent. Whereas if we initialize a forecast prior to May 1st, we cannot. So there appears to be sort of a barrier of prediction skill corresponding to roughly May 1st in this system. And I'm going to get into this issue a lot more deeply in kind of the next part of the talk. Okay, great. Actually, that is the end of that section. So the answer to have we is also yes. The current sea ice prediction systems do have some skill for capturing interannual sea ice variations, but you probably noted by now that, I quoted this number of 12 to 36 months for the predictability horizon of Arctic sea ice extent based on those perfect model experiments, whereas our current operational predictions are giving us skill at maybe 0 to 6 months or 0 to 4 months. So there's still a big gap between our potential skill and what we're currently achieving in these systems. And so in this next part of the talk, I want to talk a little bit more about the future. And I'm gonna get more into this sort of spring predictability barrier issue. And so for this part of the talk, there's kind of two main motivating questions that I want to kind of center the conversation upon. Firstly, how far in advance can we make skillful predictions of summer Arctic sea ice? And secondly, what observations do we require to realize these skillful predictions? So there's been evidence shown for a spring predictability barrier in two different climate models. I showed you some evidence from the GFDL floor model already. And there's also been some evidence shown in the HADGEM 1.2 model as well. And so a natural first question you can ask is just, is this barrier robust across other climate models? And so in order to attack this question, we need to first think a little bit about what are the key sources of predictability for summer sea ice area. And what I'm showing here in the top panel is perfect model prediction skill. So this is perfect model anomaly correlation coefficient, anomaly correlation coefficient values from perfect model experiments performed with the GFDL floor model, focused on the East Siberian and Lapte seas. And so you can see that there's some skill in these perfect model experiments. And then what the second panel is showing is if you just do something very simple, which is that if you take a simple linear regression-based model where I'm going to use earlier sea ice volume, earlier regional mean sea ice volume as a predictor of future sea ice area. And if you just look at those correlations between sea ice area and earlier sea ice volume, you get the following plot. And what I want to note, which you can probably see by eye quite clearly, is that these two panels look quite similar to each other. And so this is saying that sea ice volume is the key source of predictability for summer sea ice area predictions. And the third panel here is showing the difference between the two. So you can see that there are some differences, especially at lead 0. You can see that the perfect model skill is certainly higher than what we're getting from these volume-based correlations. However, at leads 1, 2, 3, and 4 months, this volume-based regression prediction is capturing most of the skill that we're getting in the full perfect model. And so the nice thing about this is now this gives us a method to assess the predictability of different GCMs in a diagnostic sense. So we no longer need these perfect model experiments, which are very nice for evaluating predictability, but not every GCM has them. And now we can just simply evaluate predictability using sort of this diagnostic correlation analysis between sea ice area and earlier sea ice volume. Okay, so this is exactly what we did. Oh, and I should mention actually that this work was led by Dave Bonin, who's now a grad student at Caltech, and he did this work as part of a summer project with us at GFDL a few years ago. And so what Dave did for his project was he took CMIP5 model control runs, pre-industrial control runs, and he computed these lag correlations between sea ice area in different target months and earlier sea ice volume. And so if we just look at one of the CMIP5 models, here's the access model. And you can see that you see quite a clear diagonal correlation structure coming out in that model. And anywhere you see a square on this figure indicates the timing of maximum decorrelation for a given target month. And you can see that there's a consistent maximum decorrelation that happens going from the month of June to the month of May for each of these target months. So in other words, there appears to be a barrier of predictability corresponding to roughly the month of May or June in this model. Here's the same plot for the CAN ESM2 model. Again, we see this diagonal correlation structure popping out quite clearly. Here's the same thing for the GFDL ESM2G model. Again, a fairly similar correlation structure. And then we can go ahead and we can turn the crank for the full CMIP5 archive. And what we find is that this diagonal correlation structure appears quite robustly across nearly all of the CMIP5 GCMs. Now, there are some differences, of course, in terms of the magnitude of the correlations, as well as the timing of this barrier across these various models. But I would argue that sort of in the world of CMIP5 comparisons, this is actually quite a robust feature. You know, in most models, you see a fairly similar diagonal correlation structure that comes out. And there's only a few models, such as this one, where you don't really see any sort of barrier type structure. But pretty much all the other models, there's at least some sort of barrier that appears to be there. So this might be somewhat surprising for you. It was certainly a little surprising for us how robust it was. And it was a bit surprising because we know that all these CMIP5 models have very different sea ice physics formulations. They have very different sea ice extent and sea ice volume mean states. So you might expect that this barrier mechanism could be represented well in some models, but not in other models, for example. So this kind of raises the obvious burning question of sort of what is the physical mechanism for the spring predictability barrier? And so to get at that question, what we did was a careful sea ice mass budget analysis using daily data from two different large ensemble experiments. So in particular, we used large ensemble data from a large ensemble run with the GFDL floor model and a large ensemble run with the CESM1 CAM5 model. And in each of these models, they're forced with historical and RCP 8.5 radiative forcing. And in both of these models, the sea ice mass evolves according to a mass tendency equation that involves terms related to top melt, bottom growth, and sea ice mass transport convergence. So this mass transport convergence term is the sea ice dynamics term, and then these other terms are related to the sea ice thermodynamics. And then I'm going to show three different diagnostics, one called melt, which encompasses both top and bottom melt, growth, which encompasses both congelation and frazzle sea ice growth, and then an export term, which is this mass transport convergence term. So just to give you a feel for how these mass budget terms look in this region, I'm focused on the Lapte Sea here. In both models, we can see that the models lose sea ice mass in the summer due to melt. They gain sea ice mass in the fall and winter due to sea ice growth. And then the green curve shows that the export term. So one thing you'll notice is that even in the climatology, this daily export term is quite noisy. And that's because this export term is being driven by a lot of synoptic variability in the atmosphere. So it's just a very noisy field in general. Nevertheless, we see qualitative similarities between the models, with both models losing sea ice mass in the winter months due to sea ice export. So this is saying that ice is being moved out of the domain on the mean in the winter. Okay, and then what we can do with this now is we can take this mass tendency equation and we can time integrate it. And then we can take these source terms on the right-hand side and break them up into a climatological contribution and an anomaly contribution. And then what that lets us do is reconstruct the sea ice mass time series as a climatology plus anomalies due to growth, melt, export, and then the initial mass anomaly. So just to give you a feel for how those those various mass budget terms look. Here I'm showing the sea ice mass evolution. And I'm plotting this in terms of thickness units. So you can think of this as, the thickness anomaly averaged over the whole region. And I'm showing that the evolution just for one particular year, for one particular ensemble member, going from October 1st through to the following October 1st. And what you can see is that we start off with a modest positive thickness anomaly. And then over the course of this year, we're going to develop a much more notably positive thickness anomaly. And now we can look at the various contributions from these sea ice mass budget terms to this overall anomaly. So here's the sea ice growth term. And so you can see that sea ice growth is certainly not driving this time series. If anything, the growth term is actually acting to dampen the anomaly away. So it's, the growth term appears to be acting as a negative feedback on the positive thickness anomaly. And this is consistent with the well-known negative feedback that exists between sea ice thickness and sea ice growth rates. In particular, if ice is thicker, it grows more slowly, and so that provides a restoring towards the model's climatology. Okay, so the green curve here shows the sea ice export term, and you can see by eye that there's a very clear correspondence between the magenta time series and this green time series. So it's really the export term that's dominating the high frequency variability of this time series. And it's also driving the sort of longer timescale, multi-month increase of sea ice thickness as well. And you can see that the export term, it sort of almost looks kind of like a random walk through the winter months. So it's sort of bouncing around fairly randomly. Nevertheless, you eventually build up some anomaly in thickness by the start of May. And that timing is very critical because the start of May is when the sun comes up in the Arctic and sea ice melt begins to kick in. And so if we look at the melt term, the melt term is off as you would expect during the winter, and then it turns on sort of in the later part of May. And you can see that the melt term, it actually is responsible for driving this very large increase from a thickness anomaly of around, maybe half a meter to an anomaly closer to a meter. And so there's this rapid increase in thickness, which then persists throughout the summer months. And then if we look at sea ice concentration, which is what we're trying to predict, this thickness anomaly is giving us a corresponding anomaly in sea ice concentration. So we're seeing a positive sea ice concentration anomaly, which is coming from this anomalously thicker ice, which is reducing the sea ice melt in the summer. So kind of putting this all together, this is suggestive of a mechanism for the spring predictability barrier. The sea ice mass in winter is driven by these relatively unpredictable export variations, which are dominated by synoptic atmospheric variability. And it's hard to know what this green curve is going to do. Nevertheless, it kind of wiggles around and it eventually gives you some anomaly in the beginning of May. At that point, the sun comes up in the Arctic, and then via positive ice albedo feedbacks, the melt term is going to act to take whatever anomaly you have and enhance it. And that's due to positive ice albedo feedbacks coming from both thickness as well as sea ice aerial effects. And then after we get that big positive ice albedo feedback, we have a large thickness anomaly, which is able to kind of persist through the rest of the summer. And then we're left with the thickness anomaly at the end of summer, which gives us a corresponding sea ice concentration anomaly. Now we can look at this a bit more carefully by doing a sort of rigorous covariance decomposition, where we can look at the covariance between sea ice area on September 1st and earlier sea ice mass anomalies. And this decomposition of covariance basically confirms what I just kind of explained qualitatively, that the time of year where you see the rapid increase in covariance between mass and area occurs over the months of May and June up to July. And this rapid growth in covariance corresponds to the time when the melt term turns on. And this melt term is what actually is driving the rapid growth in covariance that we see over the melt season. And this is the case in both the floor model as well as the CESM model. And so what this means is that the timing of the spring predictability barrier is set by the timing of sea ice melt onset. And so you tend to get this rapid growth in predictability when the melt term turns on. And what that means is that if the melt onset timing were to shift at all, then you would get a shift in the predictability characteristics of the sea ice. And if you squint hard at this plot, you can see that the melt term turns on in floor around May 15th, whereas it turns on a little bit later around June 1st in CESM. And if you look at the barrier structure in these models, there's a corresponding roughly 2-week shift in the spring barrier timing, with CEM's barrier being about 2 weeks later than floors is, corresponding to the slightly later melt onset in the model. Okay, so this has some important implications for the construction of sea ice prediction systems, in the sense that the fact that we get this rapid increase in predictability after June 1st suggests that having thickness observations between June 1st and September 1st would be especially valuable. Unfortunately, the current satellite observations of sea ice thickness span a time period of roughly October 15th up to April 15th. And critically, they terminate prior to the timing of this spring predictability barrier. So this says that these thickness observations likely don't have that much value, at least for predicting regional sea ice area anomalies in the summer in the Arctic. And if we want to really maximize our predictability, we need to try to extend these thickness observations as far as possible into the summer. Ideally up to June 1st, but preferably even later than June 1st would be even better. And we're currently working with folks in the remote sensing community to try to do just this. Great, so that was what I wanted to say today. So I'll just leave you with a few concluding thoughts. So the past decade of sea ice prediction research has featured an identified need for seasonal to interannual predictions of Arctic sea ice. There's been a clear demonstration of potential sea ice predictability, and it's also featured the development of skillful dynamical and statistical seasonal sea ice prediction systems. There's still a lot of room for improvement, and these future improvements will require integrated efforts between the modeling and observational communities, specifically asking the question of what observations do we need and when. We also need more research on the inherent predictability of Arctic sea ice. What are the opportunities? What are the limitations? We need improvements on forecast initialization, and we need to reduce our model biases. And we also need to develop and incorporate more user-oriented forecast metrics. So great, with that, I want to say a big thanks to you all for tuning into this webinar. I'm happy to take any questions or comments you might have, and feel free to contact me. My email is listed there as well. So thanks a lot.
Great, thank you, Mitch. So we'll take the next 21 minutes for questions. If you have any questions, remember to either use the raise your hand button that's found next to your name, or you can type your question into the chat box. All right, so I see we have a question immediately from Dylan. Do you want to go ahead and unmute yourself?
Sure. Can you guys hear me okay?
We can, yeah.
Cool. Great talk, Mitch. That was really, really informative. I had a couple quick questions. I was struck in your diagonal plots across the CMIP5 archive. I was struck by the fact that some of the early initializations in the winter and spring had predictability, skillful predictability at long leads, but not so much at short leads. I think later on you sort of touched on the fact that this is probably due to the fact that all of these models have basically the same onset timing of the melt period attached to the sun. So I'm guessing that's sort of why that is. But I guess I'm just asking for clarification on that, whether the winter initialization months don't have skill at short lead times, but they do have skill at long lead times for that reason.
So are you referring to sort of these correlations kind of beyond the diagonal line up here in these plots, or?
Yeah, and even on like the third model in the third top row, third column. Yeah, you can sort of see that if you initialize in January, you have basically no skill until you get to like the summertime.
Yes, exactly. So I'm not sure I'm fully following your question, but the idea is that there is some baseline predictability that can be carried over from year to year. So that there is some year-to-year correlation of sea ice volume, but the point is that it's quite small, and the key comparison is sort of how big is the year-to-year persistence compared to sort of the more unpredictable noise effects that come from the sea ice export term that I was highlighting. So that's why we're seeing some correlations at these longer lead times, is that there is some year-to-year persistence, which the correlations might be around 0.3 or 0.4. So there's definitely something there, but it's only capturing a fairly small fraction of the variance. And it's only really once you kind of get past this diagonal line here that you really start jumping up. So
Right.
hopefully that
makes sense. Yeah.
Yeah. Does that make sense?
It does. Yeah. Yeah. I guess I was just struck by, if you just sort of broadly look at these plots, you can see there's a big orange column in the summer and springtime in every single single model that goes for all lead times. And I think
that comes from a bit of a simpler reason, is that if you look at these regions, the Lapte and East Siberian Sea are essentially fully ice covered in the winter months. So you can see that starting in December, I think this is what you're referring to, starting in December and going through to May, there's a clear drop in correlation. And that's because the region's essentially fully iced over then. And so you're getting some small fluctuations in sea ice area due to very small leads opening up and very small fluctuations, but those are essentially synoptic in nature and they're very unpredictable. So you're essentially trying to predict a very small signal that's essentially white noise in these months, but then you get large anomalies in the summer months when you get more open water. So that's kind of why you're seeing this difference between winter and summer. There's a big discrepancy there. So hopefully that kind of answers the question.
Sure. Yeah. Thank you.
Yeah, no problem.
And I see a couple people who raised their hand, but let's take a question from the chat first. Jean Huang says first, great talk. Does GFDL have a plan to initialize sea ice extent or thickness in the SPEAR prediction system, or is it possible with existing observations?
Yeah, great question. So we are working on that currently, and we have sort of an experimental sea ice data assimilation system, which is currently just assimilating sea ice concentration and sea surface temperatures. And we have found that we get a large improvement at short lead times. And by short here, I mean leads of 0 and 1 month. Whereas we find at longer lead times, the sea ice concentration and initialization doesn't make as big a difference. But we think on the subseasonal time scale, sort of getting the initial sea ice extent and concentration anomalies correct is very important. And then what we're currently working on is building sea ice thickness assimilation into the system, which of course is more challenging because we don't have a nice continuous record of satellite observations. And as I mentioned, the observations are only available in the winter right now, which is also challenging. But we are working on that, and we think we might be able to get some improvements by adding the thickness in as well. So yeah, great point, and I fully agree with it. I fully agree with you that it's a great idea to pursue.
Thank you. That's a good response.
Let's go to Qinghua.
Yeah, very, very nice talk. So my question is that, so do you suggest this sensitivity to thickness only work for its too small area, or how about for the other basin? So this is my question. my question.
Yeah. Great question. So one point I should have mentioned that I didn't is that the spring predictability barrier seems to apply more on the regional scale than on the Pan-Arctic scale. So there is a bit of a barrier structure to the Pan-Arctic in the sense that you do see that skill increases rapidly after melt onset, even for Pan-Arctic sea ice extent, but it's not quite as well defined as what you see on the regional scales. That being said, if you look at other regions of sea ice variability, such as the Chukchi Sea or the Beaufort Sea, or the Canadian Archipelago, or the Kara Sea, all of these have a fairly similar diagonal correlation structure to them that emerges. So I think there's something important about sort of spatial scale here. When you get down to this regional scale, the fact that sea ice is so dynamic starts to matter a lot more. Whereas when you're looking at the Pan-Arctic scale, you kind of integrate away some of those unpredictable dynamic features, in the sense that if you're trying to predict Pan-Arctic sea ice extent, you don't care as much if you blow ice from one region into another region, for example. But if you're trying to get that region's exact anomaly, then you start caring about those winds and those unpredictable features a lot more. So the answer is it's quite robust actually across most regions of summer sea ice variability.
Another question from Balasubramanya. Sorry if I mispronounced your name.
Yeah, okay. Balu for short, just because it's such a long name. That was a fantastic talk. And I was wondering if the mass balance analysis that you did in Lapte, I mean, one can imagine that can be quite different in other regions. For example, if you did this on each of the 14 subregions that you identified, I was wondering if you've done it, and if so, how typical is what you see in Lapte, or if not, why chose to highlight Lapte?
Yeah, so kind of as I was just saying to Qinghua, it's if you make sort of these plots for other regions, so in these plots again, I was showing this covariance decomposition, and what you find is that there's a very robust rapid increase in covariance that lines up with melt onset in pretty much any region you look at, and the relative magnitudes can change a little bit, so that the shape of the export curve will change. The relative magnitude of this covariance relative to the export covariance will change as well. But the general feature of kind of the rapid increase at melt onset is actually very robust, at least in these two models, in FLORA and CESM. But the fact that the barrier is so robust across all CMIP5 GCMs, to me, suggests that it's probably quite a similar mechanism that's active in other models as well. I would contend.
Okay, sorry, you may have misunderstood my question, and I may not have understood your presentation fully. So, is this for the Lapte C? And if so, I was asking about the other regions rather than the other models.
Yeah. So this plot is for the Lapte C, and what I was saying is, if you do the same plot for other regions, for example, the East Siberian Czech.
Okay, so you are saying that behavior is robust across regions as well.
Yeah, there are some differences, but the sort of the qualitative features are all very similar across the various different regions.
Okay, thanks.
Yeah, thanks.
And I see a question from Michelle LaRue.
Hi, Mitch. Really great talk here. I thought that was one of the clearest presentations I've seen in a while. So nice job with that.
Thank you.
I have to admit my ignorance is going to show a little bit here, but so in this slide you're showing, essentially that melt onset is, takes off around May, June, and then you have this export synoptic term, right, which you kind of described as somewhat unpredictable, right, because this gets into the synoptics of it. It seems like that, I mean, maybe I'm not interpreting this figure correctly, but it seems like that is like kind of the key term to get the sea ice correct. So I'm just kind of curious how much you think the thickness, like if you were able to resolve thickness well, how much that's actually going to improve our prediction of this export versus melt, and what will we ultimately get from that initialized thickness? Where are we improving there?
Yeah, great question, and I may have not explained this well enough, but I think both the export term and the melt term are completely fundamental to the predictability, and you can see actually that in terms of the covariance, really it's the export term that's actually contributing more than the melt term, and it's the melt term. The melt term is kind of causing this rapid increase in covariance in the spring, but it's the export that is really kind of the dominant player, I would say. The challenge is that this export term, it drives a lot of the variability, but the problem is that the export variations are not entirely predictable. So it's very easy to, if you know your thickness on April 1st, for example, you can see that the covariance is much lower here than what it's going to be later on in the summer. And what this is saying is that basically you need to know what the atmosphere does between April 1st and July 1st in order to get meaningful information for predictions. So there was some information present on April 1st, and it is growing monotonically, but it's kind of growing in sort of like a random walk sense is kind of how I like to think about it. There's some anomaly that is being generated, but it's quite hard to actually get the details right. And it's only kind of once you get far enough into the season, which corresponds with the timing of melt onset, that the anomalies are able to kind of grow to a sufficient magnitude that they have persistence and can kind of carry through to the summer sea ice minimum, which is why we see much more covariance here. So it's kind of this interesting trade-off between anomalies being really driven and generated by export, but then it's the, this is fairly unpredictable, and it's the melt term that acts to kind of lock it in. So, you have some random anomaly, and it's the ice albedo feedback, which is very predictable. And so whatever anomaly you have, the melt term is going to act to make sure that that anomaly gets enhanced and kind of locked in throughout the rest of the melt season. So,
I feel like that was an excellent explanation. I feel like there's so much similarity with INSO prediction here, because on some level, that's what we're kind of waiting for is sort of the lock-in of climatology. That is the SST gradients across the tropical Pacific. And it isn't until like late summer that we really get at that, because the cold tongue is maximizing at that point, and then all of a sudden you get all this predictability. There's a lot of interesting similarities and parallels here. So
there are, yeah.
I was like, I wonder how I can make this plot for ENSO.
Yeah, that'd be cool to do. I would love to see something like that.
No, it's really informative.
Oh, and then I think I didn't really answer the second part of your question, which was related to the observations. So the observations currently terminate in mid-April. And the observations would be capturing, they're sampling, you're getting a satellite swath every 90 minutes, and you get sort of a rough map of the Arctic every two days or so. So you would be sampling this sort of weather timescale variability in the thickness. So you could initialize the thickness very accurately up to the middle of April. And just the problem is that, unfortunately, we're kind of down here on our covariance curve at that point, and we haven't really climbed the mountain yet. So if we could get the data, we do have the data, but we just can't process it yet. But if we could work on the algorithms to process it and get thickness observations sort of into these summer months, we think we could probably climb up this mountain and really improve the predictions.
Thanks so much.
Okay, great. I think Mike Patterson had a similar question, which I think you just answered, but I'll just ask it again in case you want to be a little bit more thorough. He asks, why are satellite thickness observations restricted to winter months? Is there a technical challenge to overcome to extend such observations into spring and summer?
Yeah, so the reason for that is due to melt ponds that form on the sea ice. So I had a picture. So in the summer, you get surface melt, and you get the formation of these melt ponds due to snow melting on the ice. And these satellite algorithms rely on doing altimetry, like radar altimetry, for example, between the sea surface height and the sea ice freeboard height. And so what you rely on are these small little gaps in the sea ice called leads, and then differencing the sea surface height from the sea ice freeboard height. And then you can, making some assumptions about the snow, you can back out how thick the ice must be. So the problem in a nutshell is basically when you get these melt ponds forming on the ice, you can't tell what is a lead and what is a melt pond, and the algorithms all kind of start breaking down. And the satellite people have a lot of great ideas of how to fix this, but it's a challenging problem, and they're working on it still. But I think that based on our conversations, there is hope to extend it, but it's gonna take some serious work.
Thank you. So I see we have 5 minutes left, and there are 2 people who have raised their hands. So let's try to tell. Hyan, you might want to. I don't know if you still have your question, but we'll take this question from Dylan first, and then Hyan, if you still want to ask your question, we can take your question. So Dylan.
Sorry, just one quick follow-up question. Is there interannual variability in the melt onset timing? And if so, is there something predictable about the melt onset timing interannually that might extend prediction into the winter?
Great question. Yes, there is a lot of interannual variability in melt onset. And the interannual standard deviation would be on the order of 2 weeks or so, something like that. So
not much.
So not huge, like we aren't talking about many months, but this curve can definitely bounce around year to year. And actually there was one study that I showed.
Or even decadal variability would be interesting as well.
Even decadal, yeah. So this study here used spring melt pond fraction on Arctic sea ice as a predictor of September sea ice, and it does quite well as a predictor. And so it's basically capitalizing on exactly what you said, the interannual variability of melt onset, and the fact that if you shift melt onset a little bit, then the ice albedo feedback kind of grabs onto that anomalously early or anomalously late melt onset, and it tends to lock it in and sort of enhance whatever anomaly you have. Now, so we haven't assessed this super rigorously. I've looked at it somewhat myself, and I found that melt onset interannual variability is not very predictable. So it's mostly driven by synoptic atmospheric variability. There are some trends as well. So we do have a trend towards earlier melt onset, but the trend signal is somewhat swamped by the signal of just the interannual weather variability, essentially. So I think it's mostly a weather issue right now. And so kind of once you know it, it's a useful predictor, but you can't know it too far in advance is kind of my feeling on that. But it's a great question.
Right. And I guess knowing the onset to the day is not as impactful as knowing like monsoon onset to the day. So 2 weeks on either side probably isn't as big of a deal.
Yeah, I mean, it does matter, like in the sense that, like this skill kind of coming from those 2 week differences. So it is relevant. It's just a question of, is it predictable? Is it predictable, or is it more something that we just kind of need to observe and then initialize and kind of put it in, which would also be valuable. But whether or not we can actually predict it from the winter, I would expect the answer is no, because if we could, we would find that we would have more predictability for sea ice regionally from the winter, from the previous winter, basically. But we aren't seeing that, so I suspect that it's not that predictable. But still more work to be done on that question.
Thank you.
Yeah, thanks.
All right, let's take this final question from Haya before we wrap up.
Nice talk, Mitch. Can you hear me?
I can, yeah.
Oh, yeah. Okay, you mentioned actually your talk is about the predictability depends on the mean climate, and in your talk you mostly focused on how predictability property is changes with annual cycle. But I'm just wondering whether you could comment on how predictability is affected by the changing mean climate, because here we're dealing with a fast changing mean climate, and is there any evidence showing some regions or variables are getting more or less predictable?
Yeah, that's a great question, and there's been a lot of conflicting research on that question, actually. So some models have shown that predictability is expected to decrease in a warming climate, and the reason for that is that as the ice thins, it typically gets less strong and it becomes more mobile and starts flowing faster. And the ice is therefore more susceptible to the unpredictable aspects of the atmosphere. So, that argument is kind of suggesting that predictability should decrease in a warming climate. However, there was a recent study, which maybe you've seen this actually, that was led by Marika Holland, that came out in, I think, Journal of Climate last year. And she found that predictability actually is very non-monotonic in time, in the sense that it was lower in the 1970s and 80s, and then increases to a local maximum around the year 2020, and then starts to decrease again. And the reason for it was kind of this complex interplay between thickness anomalies and their coupling with sea ice extent anomalies. And so if your ice is too thick, then your thickness variability may not be able to impact sea ice extent variability. Whereas if you're sort of in the sweet spot, then a given thickness anomaly can really manifest as a large sea ice extent anomaly. Whereas if you're too warm, you just have no thickness left and you just tend to melt all the ice away. So you lose all the predictability. So there's these very interesting sort of non-monotonic state-dependent behaviors in predictability. So the answer to your question is that I think we don't really know yet. It's quite complicated, and work has suggested we might be around the maximum of predictability right now in the current climate, but still a lot of work to be done to really tease that out, I would say.
Thank you.
Yeah, thank you.
All right, I think that will wrap up our PPAI webinar. So thank you so much, Mitch, for your talk. And also thank you to Qinghua for organizing the talk. I know he had to leave a little early today, but I just want to give him a shout out. Just a heads up, the next PPAI webinar will be on March 17th. So I'll send out more announcements once we have those details. But thank you everyone for participating as well.